Okay, so in part one version of this video in deriving the C5 character table, we did all this work and we got to this stage. We're actually able to assign Mulliken symbols. We figured out functions transformed. We had a problem where we had five classes, but only three irreducible representations, three vectors. We know that can't be true because the number of columns and the number of rows has to equal the same thing on the character table. Also, we know the sum of the squares of the diagonals the sum of the squares of the dimensionalities, um, which is the character under the identity, has to equal the order of the point group, which is the number of symmetry operations in the point group, which is 5. 1 plus 1 plus 1 plus 1 plus 1 is 5. But 1 squared plus 2 squared plus 2 squared does not equal 5. So we have a problem. And so what we have to do is get into imaginary numbers. We have to break up these E1 and E2 vectors into imaginary components. And so we're going to start off with the E1 vector. And the way we're going to do that, so actually we know this is going to be wrong, this one here. I'm going to cross it out. I'm going to cross it out right now. But we keep it there so that we know what they're equal to. The sum has to be equal to. We're breaking this up into components now, where the sum of the two components is going to be equal to 0. Is going to be equal to whatever the original vector was, E1. So here we have 1 plus 1. The dimensionality is going to be 1. That's going to get us 2. And this one's also going to break up into 1 and 1. So now we'll have 5 rows, right? We'll end up with 5 rows, and we'll end up with 1 squared plus 1 squared plus 1 squared plus 1 squared plus 1 squared equals 1 plus 1 plus 1 plus 1 plus 1. So that rule is satisfied as well. Okay, so then the problem is we don't know what these other values are, okay? And so there's a variety of different ways you can go about this. All of them are pretty painful. In this case, the easiest ends up to be to actually think about or test some other functions, this time functions that are actually imaginary. And actually the simplest function that you can think of that works or that does something interesting is going to be x plus iy. You can do various permutations on this and you'll get something that will work as well. But we're going to do x plus iy. There's other ways to solve this using the other character table rules where you get a system of equations. I did that for the C4 and the C3 character tables. But in this case, it ends up being the easiest to do x plus iy. This is one of the more math-heavy character table derivations that you can do. So it's actually quite tricky. So x plus iy. So how is that going to transform? Well, let's recall how, well, first of all, how is it going to transform on the identity? Well, that's not very interesting, right? X plus iy is just going to go to itself, x plus iy. But when we get to the C5 operation, we're going to run into some trouble because we need to figure out, well, how x and y transform. They're not just going to transform for themselves. So we go to our handy-dandy rotation matrix, right? xy transforms to C5 as 2 cosine 2 pi over 5. And then minus 2 pi over 5. Boy, I did not leave myself enough room here. And then sine 2 pi over 5 and cosine 2 pi over 5. Okay, so what that tells us is x goes to cosine 2 pi over 5 x and y minus sine 2 pi 5 y. And so that's fine. And now what does y transform to? Well, we just look here and we're going to times each of those by I, right? So it looks like plus I sine, put an I there, and then right here, sine 2 pi over 5 plus I from there, cosine 2 pi over 5, sorry, 2 pi over 5 x, right? Plus I cosine 2 pi over 5 times y. We're doing matrix multiplication here. All right, so now let's factor some things out. And so what we can factor out is factor out the x, factor out an x. So we're going to end up with this equaling cosine 2 pi over 5 plus I sine 2 pi over 5 times x. And then if we factor out the y component, we're going to end up with cosine 2 pi over 5 I minus sine 2 pi over 5, that whole thing times y. Okay, and so if you look at this, you'll notice something quite interesting, which is this value there. That value is actually screaming at you Euler's formula. Euler's formula, if you remember, is e to some value equals cosine of that value plus I sine that value. So this actually in green here is equal to e to the 2 pi, sorry, e to the, sorry guys, e phi I. Yeah, I forgot the I there. E phi I equals cosine phi plus I sine phi. So this value here is in that form. And so it's telling you that in this case, phi is 2 pi over 5. So this is equal to simplified to e to the 2 pi over 5 I. And so the question is, is this something that we can just simplify? And is it possible that this value is actually what is being factored out here? And it turns out the answer is yes. I will prove it to you, but this actually equals this times itself, which is really nice. And I'll prove it to you in a second. But what's nice about this is that now we have x plus iy going to something times itself. We have an eigenfunction, basically. And so we can plug in a value for the character right away with a 1-by-1 matrix, right? We don't have to do 2-by-2 matrices because we're in 2-by-2 matrices, we're back to where we started. So let's just prove that this is true. So of course, this first part is true. We just saw that e to the 2 pi over I times x equals this. But does e to the 2 pi I plus times iy equal this? And the answer is yes. If we go over here, maybe in a different color, I can just show you that. But you're going to end up with first the definition of e to the 2 pi over 5 I is cosine 2 pi over 5 plus I sine 2 pi over 5. And then that is times by IY. That's what we're trying to show. So that gets you IY cosine 2 pi over 5. And then you're going to get I squared y here. Well, I squared, remember, I is square root of -1. So I squared is -1. So you're going to get a minus sign there. So you end up getting minus sine 2 pi over 5y, which is exactly this term there. And then there's the IY cosine squared. There's cosine 2 pi over 5, not cosine squared, cosine 2 pi over 5 IY. There's cosine 2 pi over 5i times y. So indeed, this is true. So your 1-by-1 matrix here, basically what we have now is a 1-by-1 matrix that we can have, where we have an eigenfunction, right? I have x, we have x plus y, the function x plus y, then can be multiplied by e to the 2 pi over 5 times I, and that gives us what we were looking for. And so that's the transformation for C5. And so then we take the character, right, the trace of this matrix, the sum across the diagonals. Well, it's going to be just equal to that. It's a 1 by 1 matrix. So this is actually our value. And so a lot of this character table is going to be based on this e to the 2 pi over 5 times I. And so we're going to define a value epsilon, and we're just going to call it that. And this is what most character tables would do. So we'll just have to remember that here. I'll make it nice and big. And so this character now is actually epsilon. Okay. Now, what do we do at this point? Well, we just keep going. And so now we're going to do this for C5 2 times, right? And what is that going to do? Well, all these 2's are now going to equal 4's, right? Because we're rotating by 4 pi. So these all equal 4's. We can write them. Beauty of erasing. And at this point, you're going to get the exact same math, but what you're going to get instead is, I'm just getting my notes here to make sure that all this math ends up working out. But what you're going to get instead is just a 4 pi, right? Everything else is the same as before. Now, what is this equal to? Well, the value is going to be, again, 4 pi. A convenient way to write this in terms of this terminology here is just epsilon squared. So if you imagine, if you take epsilon squared, you square this whole thing. You just then go 2 squared, and that equals 4 pi. I over 5. You may be wondering, how does that math really work out? Because am I going to not get a pi squared, I squared, and 25 down there? Well, if you expand this all out, it does work out. And so I can show you that very quickly here, or relatively quickly. So we know e to the 2 pi I over 5 is equal to cosine 2 pi over 5 plus I sine 2 pi over 5. Now, if we square that, what do we get? Well, we get cosine squared 2 pi over 5. Now we have an I sine 2 pi over 5 times I sine 2 pi over 5. That gets us I squared, which again was equal to -1. So it's minus sine squared 2 pi over 5. And then we have 2 terms here, 2 cosine 2 pi over 5 times sine squared 2 pi over 5 times I, right? And so at this point, you have to recall the relationship that I went over in the last video, which is that cosine squared x minus sine squared x equals cosine 2x. And so this part down here becomes cosine 4 pi, okay? And then there's also a relationship which is that 2 cosine 2 pi over 5 times sine 2 pi over 5 is actually equal to sine 4 pi over 5. So that ends up, and you can plug this into Google if you don't believe me, but just different relationships here. So that equals, so we still have the I, so that ends up equaling the definition of Euler's formula, and so we get e to the 4 pi over 5i. And so yes, epsilon squared is actually equal to our character here. And so up here, we can just put epsilon squared. Okay, so we move right along, and we're going to use similar mathematical tricks here. Now, if we do a C5 3 times, we are going to get 6's everywhere here, right? 6's. I'm not going to erase them all this time, but we're going to get 6's, 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 and we're going to get a 6 here, and our character is going to be e to the 6 pi over 5 I. And if we want to get that, into something looking nice, what will end up happening there is, what will that equal? Well, again, we use Euler's formula. So cosine, that's going to equal 6 pi over 5 plus I sine 6 pi over 5. And if we use the relationship that cosine 6 pi over 5 is equal to cosine 6 pi over 5, I went over this in the last video, is equal to cosine in part 1 of this series on the C5 derivation. Cosine 6 pi over 5 equals cosine 4 pi over 5. So this equals cosine 4 pi over 5. And lo and behold, sine 6 pi over 5 actually equals negative sine 4 pi over 5. So we put a negative sign there, and we get sine pi 4 pi over 5. Well, this looks very similar to e to the 4 pi over 5i, but we have a negative value for the imaginary component. In fact, it's the same. So e to the 6 pi over 5 over I equals e to the 4 pi over 5 over I, except we have a negative component. We call that the complex conjugate. We use an asterisk notation. So that is equal to epsilon squared, right? Epsilon squared was equal to this. That was what we found out just a moment ago. And so this is equal to the complex conjugate of epsilon squared. So that goes right in here. Okay, so at this point, we just keep cranking along, and we do a similar sort of logic. We're at C5 4, we have to figure out. And so we're going to have values here now are going to be 8 pi over 5. And 8 pi over 5 is going to end up in our final answer. And what's going to happen? We are going to get, trying to get this into a nice value here, we're going to get e 8 pi over 5i by Euler's formula is cosine 8 pi over 5 plus I sine 8 pi over 5. And we can use the relationship that cosine, lots of just tricks here, getting this nice and compact. Cosine 2 pi over 5 equals cosine 8 pi over 5. And so this becomes the cosine 8 pi over 5 can become a cosine 2 pi over 5. And we also have another trick up our sleeve, which is that sine 8 pi over 5, which we have here, is actually equal to negative sine 2 pi over 5. 2 pi over 5. And so this becomes sine pi over 8 pi over 5 becomes negative sine, so I have a negative there still, negative sine 2 pi over 5. Well, what is that? That looks very similar to epsilon, which if we remember is e to the 2 pi over 5 over I, except, right, epsilon is this guy, cosine 2 pi over 5 plus I sine 2 pi over 5. But we have a negative value because we take the complex conjugate of it. So it's going to be the complex conjugate of just epsilon. So now we have this nice character just in terms of epsilons and epsilon squares and the complex conjugates of those. Okay, so at this point, what we can do is use a simple relationship, and I'm going to erase some of what we have written here. Actually, I think if I'm careful, I can erase all of this and just rewrite our conclusion, which was we were breaking this up, this E value. We said these guys were wrong, right? This E1 was wrong. So we crossed this out, and we broke this up. We're in the middle of breaking this up into components. And if we remember all this one we just did last was complex conjugate of epsilon. And this was epsilon, and this was epsilon squared, and this was epsilon squared complex conjugate of epsilon squared. So now we can do something very easy and just to relatively easy. I mean, this is all pretty hard. Epsilon, remember, is 2 pi over 5I. And remember Euler's formula. E to theta I equals cosine theta plus I sine theta. So now what we can do is we know 1 plus 1 equals 2. These components have to add up to one another. So E epsilon plus, we'll call it A, and B and C and D, we're trying to find these. Epsilon plus A is going to be equal to 2 cosine 4 pi over 5. Just subtraction. I like that. So A equals 2 cosine 4 pi over 5 minus epsilon. And epsilon is minus cosine 2 pi over 5 minus 2I sine 2 pi over 5. And at this point, we made a small mistake here, and it's going to cause us problems anytime in math. You make a little mistake. Epsilon plus A, we're doing vector E1 here, not vector E2. So I confused myself by crossing this out, but it's not going to be in the character table in the end. What's going to be in the character table is E1. But this is supposed to be a 2 here. Right, we want the sum to equal 2 cosine 2 pi over 5, not this one. So down here is going to be 2 cosine 2 pi over 5. And so A is going to equal to, now we have 2 cosine 2 pi over 5 minus cosine 2 pi over 5. That's cosine 2 pi over 5. And why did I have a 2 here? Shouldn't have a 2 here. All we are doing here is saying A equals 2 cosine 2 pi over 5 minus epsilon. And so epsilon doesn't have a 2. It's just, epsilon is just cosine 2 pi over 5, right? It's e to the 2 pi over 5 over I minus I sine 2 pi over 5. So anyway, this is now correct. And we get this. Well, what is that? That looks very similar to epsilon, except we have a negative sign. That is equal to epsilon complex conjugate, right? We have a negative sign for the imaginary part. So this value now we solve for relatively quickly as epsilon complex conjugate. Okay, so now we can do a similar thing for epsilon squared plus b. Hopefully we won't make a mistake this time. it's going to have to equal to the sum. Remember, we broke this vector up into components. So the two components have to sum up and equal to what we originally had for E1. And that was equal to now 2 cosine. This one is 2 cosine 4 pi over 5. And so now B is going to equal to 2 cosine 4 pi over 5. And remember, earlier we said that epsilon squared ended up just being e to the 4 pi over 5i. We had to do some math to prove that that was true, but that was true. And of course, that is equal to cosine, by Euler's formula, cosine 4 pi over 4 pi over 5 plus I sine 4 pi over 5. So we are subtracting that out. And what do we get? Well, we get that B is equal to just 1 cosine 4 pi over 5, because we have 2 of them, minus 1 of them, minus I sine 4 pi over 5. Well, that looks very similar to epsilon squared, which is e squared, which is this, right? Except it's the complex conjugate of it, again, because we have just the negative part, the imaginary part being a negative. So B is equal to epsilon squared complex conjugate of epsilon squared. So we can fill that in. And then let's do C. So C, we have that the complex conjugate of epsilon squared plus C has to be equal to 2 cosine 4 pi over 5. Very similar sort of thing here. Now we know what complex conjugate of epsilon squared is. So C is going to be equal to 2 cosine 4 pi over 5. We have to subtract the epsilon squared complex conjugate, which is minus cosine 4 pi over 5 plus now I sine 4 pi over 5, which just equals 1 cosine 4 pi over 5 plus I sine 4 pi over 5, which is what epsilon squared is equal to. So this equals to epsilon squared. We figured out our value of epsilon squared. And relatively speaking, we are screaming along, right? And our last one is epsilon complex conjugate of epsilon plus d has to equal to 2 cosine 2 pi over 5. And so d equals 2 cosine 2 pi over 5 minus the complex conjugate of epsilon, which is cosine 2 pi over 5 minus I sine 2 pi over 5, which equals cosine 2 pi over 5 minus I sine 2 pi over 5. And we had to minus the complex conjugate. So we actually had a minus here. So this should have been a plus. So this is a plus. And that is equal to epsilon, right up here. So d is equal to epsilon. So that goes right here. Okay, so now I'm going to erase this and I want to talk a little bit about what we have to do next. We're not quite done. We did a lot though. The last step that we have to do is we have to pick up E2, right? Because that one's also, I mean, that's very unfortunate and pretty rare that you have two vectors, irreducible representations, and both of them have to have imaginary numbers. So we have to break this one up. This is why this is a lot of work, this C5 character table. We have to break this up, and again, it's going to have to be 1 and 1, because 1 and 1 plus 2. We're trying to have it sum up to E2. And so you could do, very similar work that we did in this video from the beginning. You can't use the function x plus Iy to help you, as we did over here, you'd have to use an imaginary function that had xy and x squared minus y squared. So it's going to get pretty bad. There's an easier way, though, and you can just look at patterns here. Look what happened when we had a very similar looking function here. It's just that 2 cosine 2 pi over 5 was on this position, and now it's on this position. And we have 4 pi over 5, 2 cosine 4 pi over 5, it's on this position. You know, these are equivalent, right? These are equivalent. These are equivalent. We're just crisscrossing here, and these are equivalent. And look what happens. Every time on E1, we had epsilon plus complex conjugate of epsilon. That's how we had to break it up if we wanted to be equal to 2 cosine 2 pi over 5. If we wanted to be equal to 2 cosine 4 pi over 5, we had to have the complex conjugate of epsilon squared plus epsilon squared. Same thing over here, right? 2 pi over 5, we have complex conjugate of epsilon. And look how they alternate here, right? So crisscross. So we just want to keep these same patterns going on where we crisscross and crisscross, okay? And so that's all we're going to do to save us a ton of time. Sometimes it just helps to look at patterns. The math is going to end up being the same. So look, here we're trying to get equal to, now with E2, 2 cosine 4 pi over 5. So we need one of these vectors, and it doesn't really matter which one, right? Because this is sort of arbitrary, which one we put first and which one we put second. It's totally arbitrary. We just know one of these is going to be epsilon squared, and one of them is going to have to be complex conjugate epsilon squared. We could write it the other way, but if we choose to write it this way, now we're locked in, and we got to get the pattern right. So now this is going to mean our next one, we're summing up to equal 2 cosine 2 pi over 5. So we're going to have epsilon plus epsilon complex conjugate. And notice that the epsilon was across from the epsilon squared here. So that's the way that we're going to want to do it. And we can think about this a little bit. Let's hold off on that actually for now. Let's do this side. So this side, we saw that they were flipped, right? And so this is going to be 2 cosine. We're trying to equal to 2 cosine 2 pi over 5. And so that one is also going to be just epsilons. We have to think about where the complex conjugate is going to be. This one is going to be 2 cosine 4 pi over 5. So that's going to have the epsilon squares. And the complex conjugate has to be opposite so that we crisscross, right, to maintain the pattern. And then for the last one, you can see also that we crisscrossed. And in particularly, if we just keep the pattern here, this one's going to have to be complex conjugate, and this one's going to have to be a complex conjugate. And there's different ways that you could work through this. Again, with orthogonality, of course, these are going to have to equal to the values that we have. But you know, it's just a lot of the same sort of trigonometry. So I think we'll call it quits there. Here it is, and you can see these patterns that I'm talking about, and how you have to have also unique vectors is another point. So when you're thinking about this, here you have a vector that's epsilon squared, complex conjugate, and epsilon complex conjugate. Nowhere else do you have that. And so, you know, all your vectors also have to be unique, right? You can't be doubling up. And so that's another thing that, you know, you can watch for.